In Lecture 11, we will cover Section 4.4. At the end of today's lecture, you should be able to apply node voltage analysis to circuits with dependent sources. By adding a dependent source, we must express the behavior of that source in terms of our node voltages. That is, our number of KCL equations still holds true as our number of nodes minus number of voltage sources minus unity being the number of KCL equations we must resolve. And our supernode formulation is still valid. That is to say, nothing changes with a dependent source added to our circuit when we are using node voltage analysis. To illustrate this, let's look at example 1. We want to use node voltage analysis to determine the node voltages within our system. We have Ix, which runs through our 6 ohm resistor that is between terminals A and B. We have a current controlled voltage source that exists between terminals C and D, such that its voltage output is going to be proportional to 3, the gain, times the quantity Ix. To begin, we'll assign our nodes labeled A, B, C, and D, where D represents our ground, as well as leg currents to all branches within our system. Ix was given as the current running between nodes A and B, and we will prescribe ID as the current running between nodes C and B through our 3 ohm resistor. Step 2 is to assign voltage potentials consistent with our passive sign convention, where V1 corresponds to our 6 ohm resistor, where its polarity is dictated by the directionality of Ix, and V2 corresponds to our 3 ohm resistor, where its polarity is dictated by the directionality of ID. We have 2 dashed segments, one between nodes A and D, and the other between nodes C and D. Between nodes A and D, we recognize we have an independent voltage source, and between nodes C and D, we recognize we have a dependent voltage source. Step 3 is to apply our requisite number of KCL equations to our non-zero and non-specified nodes. Nodes A and C are specified. That is, the voltage at those nodes is going to be dependent upon our independent and dependent sources respectively. Node D is ground, such that the only node we have left to apply our KCL equation would be B. Since we have 4 nodes, 2 voltage sources, and unity, we need only one KCL equation, which will be applied at B. Our KCL equation at B can be stated as follows. Ix plus 2 amps plus ID is equal to 0. Step 4 is to apply Ohm's law to our KCL equation in terms of our node voltages. That is, Ix can be expressed as VA minus VB per 6 ohms, plus our 2 amps entering, plus ID, which can be expressed as VC minus VB per 3 ohms, is equal to 0. We have one equation and 3 unknowns. The other 2 equations are going to come from our independent and dependent voltage sources. We have 2 voltage source equations that will provide the additional equations needed to solve for unknowns. Starting with our independent voltage source, we have 8 volts is equal to VA minus VD, where VD is equal to ground. Thus, our node voltage at A is equal to 8 volts. Our second voltage source equation comes from our dependent source, such that we can solve VC in terms of Ix. We see on our dependent voltage source that we'd have 3Ix would be equal to VC less VD, where VD is equal to 0, such that VC is equal to 3Ix, where 3 is the gain of our current controlled voltage source that has units of ohms, and Ix is expressed as VA minus VB per 6 ohms. Therefore, VC would be equal to 3 ohms times the quantity 8 volts minus VB per 6 ohms. Or VC is equal to 4 volts minus VB per 2. Now we have an expression for VA, expression for VC in terms of VB, and our KCL equation that had VA, VB, and VC. Going back to our KCL equation where we had Ix plus 2 amps plus ID is equal to 0, we can substitute in our known values. Ix, which was represented as VA minus VB per 6 ohms, where VA is equal to 8 volts, now becomes 8 volts minus VB per 6 ohms, plus for 2 amps entering, plus ID, which was expressed as VC, minus VB over 3 ohms, which can be expressed as 1 per 3 ohms, times the quantity VC, which we found to be 4 volts minus VB per 2, minus VB per 3 ohms, is equal to 0. Thus, solving this equation in terms of VB, we find our voltage at node B is equal to 7 volts. Substituting this value into our dependent voltage source equation, we have VC is equal to 4 volts minus VB per 2, or VC is equal to 0.5 volts.